So let's talk about um, lengths. Planck's length. Sorry. So we'll be talking about Planck's length, time, and mass. Okay. So when we talk about these, by the way, Planck's length, Planck's time, and Planck's mass, uh, this Planck's goes with each one of them. Okay. Now, um, to talk about different kinds of things like this length, which is speed, mass, and size, we go into different kinds of theories, like different kinds of different physics theories. So when we talk about mass, the mass is all about uh, general relativity. In general relativity, we can study mass as a whole, and speed is in the department for special relativity. Okay, and uh, size. Size. When we talk about size, these both we know they are already from macro level. So it's bad. So size. When we talk about size, we're talking about the smallest fundamental level, which is quantum mechanics. So this is where we can talk about. We can get these whole, and they are and these are something known as fundamental constants, which are c, speed of light. For size we have Planck's constant, and for mass we have gravitational constant. So c, which is speed of light, h is reduced Planck's constant, sorry, and g is gravitational constant. Okay, and they are fundamental constants, they will not change, and they are this this area or this universe's fundamental constant, means you cannot change it. Reduced Planck's constant will remain the same no matter what you do. Speed of light remains the same. Gravitational constant, which we already know what the gravitational constant. Let me give you an example of each in like equation in which each of these is used. For gravitational constant, we have F is equals to G m1 m2 over r squared, and for Planck's constant, reduced Planck's constant, we have E is equals to h bar lambda h bar w, and for C we have the famous E equals to mc squared. So here only this E, h bar lambda, and h bar constant, and G, they are the only, so not M here, it's C actually. Only they are the missing the constant values. Other than that, other values are changing. Like here, force is changing when we talk about that. When we talk about which object are we comparing it to, two objects, two different objects being compared, they will be of course different. For each different object we have a different force, and for E it changes due to when we talk about different particles, and for E it depends on what we're talking about. So and so what we okay, one more thing. uh Whenever we try to define something, let's suppose length, mass, second, what we actually are trying to do is we always get this definition, the definition of second, from a physical system, that second, what second actually is, it's, if I write what second is, before, when we were in old times, there was a different definition of second, but since now that because of the increase in advancements in technology, we can get a precise definition of second, which is, which, well, let me write this, then I'll tell you how it works. Then I'll tell you what I actually mean by what I'm writing. Okay, now, so here, sorry. Now, cesium 10133 is one of the isotopes of cesium atom, and this atom, or this atom, what's so special about it is that when it has a certain excitation, it has a certain transition state. So, um, the transition here is that when, sorry. So then this value over here is 9192631770 is actually the amount of circle, or the amount of cycles this sees, this radiation in this um, atom does uh, in 1 second, is actually the definition of second is, I think that's not a proper one. The proper one is 1 second is the duration of this value over here, periods of radiation corresponding to transition between the two hyperfine levels of the ground state of the cesium 133 atom. So this is a precise value. This is a physical, physical, sorry. And even for length and for mass, we have the same thing, physical system definition. And it's for mass and length as well. So when we now that we have talked about this physical things, now we will be talking about the limit to how much we can measure length, limit to how much we can measure time, limit to how much we can measure mass, after which the space and distance in physics breaks. Now what we will be using is natural numbers, natural units. Again, natural. By natural, it means they are, now here, natural units. Again, fundamental. So which are, again, C, H lambda, and G. Okay, which is 3 times 10 to the power minus, sorry, 8, which is, and this one is 6.67 times 10 to the power minus 34. uh Wait, no, that's wrong value, sorry, minus 34, no, minus 11. H is H lambda is nothing but H over 2 pi, which is 1.05 times 10 to the power minus 34 joule second, which is not joule second, it's actually, we'll write its basic unit, kg meter square per second, meter cube per second, kilogram second square, and then we have meter per second for speed of light. Now we will be using these to get our Planck's length, which is our main thing, and then we will go for Planck's time and mass as well, but we'll not focus that much on it, because the derivation after that is easily done by it can easily be done if we know the derivation for Planck's length. Now, for Planck's length, we will be using these fundamental things again, fundamental constants with, and our main focus will be their units. We do need the value of we like we need this value, because we will then of course after that calculate that Planck's length, which we will need to see if our answer is correct or not. So how we do this is, now how do we get started? To do this, we have to go for C, G, or let me write first lambda. C H bar. I don't know why I'm saying lambda a lot. So uh, for the powers, because we know about the powers 1, 2, 3, 4. So for the powers, we will be focusing on these basic powers, lambda, sorry, alpha, beta, and gamma. We'll be using these as powers, and later on we will get the numbers which we want. Now, uh, now, now we will be only focusing on the units here. No need to look at these. For now, we can forget these. Okay, we can forget these. Now, for unit for C, which is here, is mass, so meter and second. Now, for meter is alpha, and for seconds alpha as well, because we're talking about C. And okay, then sorry, reduce Planck's constant, which is kilogram is wait for H, right? H, which we have for H is m kilogram beta. Then we have, this is how we actually write them. We write them in close brackets. I think I don't know what they like. What was okay? And then second, which is negative beta, negative, and because when we bring this s to the top, we get negative, because 1 over a is nothing but a to the power minus 1. Now m is 2 beta, and then we have g. Oh, sorry, I don't have space, so I'll just make up, let's write it in middle. uh m for g, it's m 3 gamma, power 3 gamma, kg, which is negative here, negative gamma, and then we have second, which is power 2 gamma, negative 2 gamma, of course. Now if we're talking the same, so I will go for, now we will be talking, now let's take the common coefficients. Now m is first, for m we have this one over here is for speed of light. This one here is for, wait, what is this for? Is it for, yeah, it's for Planck's constant, and this one is for gravitational constant. Now take m common first, the coefficient m common, which we give m to the power alpha plus 2 beta plus 3 gamma. This is our first one. Second one, which is second, and for second we have negative 2 negative b, sorry, not 2, it's a alpha, let me write it correctly, minus 2 gamma. And our last and not but least is kg, which is b, sorry, beta minus alpha. Now using these we will come up with our final uh, derivation, which is Planck's length. Now look at the powers carefully, because we will be using these powers to simplify our values. Now we need beta minus gamma equal to 0. This is how it should be. And negative alpha negative beta minus 2 gamma is equals to 0, and alpha plus 2 beta plus 3 gamma should equal to 1. Now if we have this, now the rule here is beta minus gamma is equal to 0. That means beta is equal to gamma. Sorry, is it gamma, right? Yeah, that's gamma. So that means when we put this in the second equation, which is beta, so it becomes negative alpha negative gamma negative 2 gamma is equal to 0, which gives us negative alpha negative 3 gamma is equal to 0. And so we get in the end, what do we get? 2 goes that side, wait, it goes that this side. Wait, not 2 again, sorry, it's alpha. So it becomes alpha is equals to alpha is what again? Uh, negative 3 gamma. And this over here, alpha plus 2 beta plus 3 gamma is equals to 1. And so this shorts up to gamma is equals to 1 over 2. And when we use this gamma in this equation, we get alpha is equals to negative 3 by 2. So these are our values of wait, so that means beta is equals to also beta is equals to 1 by 2, right? Because we substitute this equation into this. Now these are our three, now these are nothing but our powers, which we will use to which we will use with these. Of course we just calculate the powers for dc, Planck's constant, and gravitational constant, and now we can make our equation. But before making the equation, you must know that half nothing but square root of 2, and 1 by 3 is nothing but cube root of 2. And let's suppose power 1 so it's cube root of 2. I just took as an example. So if we know the powers like this, that means the powers we got here are 1 by 2 means of course a root of, let's suppose, 1, and 3 by 2 minus 3 by 2 means 1 over 3, sorry, root of 1 cube. Okay, that's how it will be for 3 power 3 by 2. Now that means our equation becomes, what's our gamma is equals to 1 by 2, sorry, 1 by 2 is that gamma, right? And alpha is equals to, sorry, alpha is equals to 3 by 2, negative 3 by 2 actually, and beta is equals to 1 by 2 as well. Now alpha is c, gamma is h, sorry, not h, g, and beta is h bar. Now since these two are squares, that means square of g times square of h, and c, since it's a negative, means we're talking about the bottom. Let me write this separately. We're talking about the bottom, which is uh, square of c of power 3. So when we combine, we get uh, square of g square of h bar over square of c cube, which can again be further. Final simplification we get is square root of g h bar over c square, because square is common now, so we can take square as a whole. Now that's our final derivation. We just got Planck's length, and when we put in the values, because since they all are constant, we don't have to measure anything, so we get a one certain or one definite value, and then this is our one definite value which will not change, and we write it as lambda, oh sorry, lp stands for Planck's length. And then what we get for Planck's length is the value which we get is 1.616, sorry, 1.616 times 10 to the power minus 35, what do you call this, meter, since it's a length, because this is the smallest length possible. It is the smallest meaningful length in physics beyond which classical concepts of physics and time break down. Means after that value, you the classical physics limit is reached. You cannot talk about classical physics after this value, beyond this value, which is known as quantum gravity and string theory. Yeah, so that's like the fundam if after which we get the most famous theory is about quantum gravity, which is for the discovery of gravitons. And at scale smaller than Planck's length, quantum fluctuations in space-time due to gravity become dominant. By dominant, I mean it takes over, making standard physics inapplicable. Inapplicable means now the classical physics in which we have some definite values change, and we reach or we enter the realm of probabilities. Beyond this, beyond this, we have probabilities. Means the quantum physics starts, and and similarly, like Planck's constant, we have Planck's mass, for which we have wait, sorry, it is mp, which is square root of h lambda c over g, and then we have t or p, which is Planck's time, and for time we have uh, square root of h bar g over c power 5, and yeah. Now you can do the calculation, you'll get these two. Now here, what's interesting about black hole, we'll just get the mass Planck's mass is that it is mass at which gravitational and quantum effects become equally strong, meaning now uh, at macro level gravity is the strongest, but when we shrink down to this amount of mass, our calculation of quantum effects are now equal to gravitation. At quantum level, gravity becomes weak. It is much larger than typical particle masses, proton mass, which is 10 power minus 27, making it unique in fundamental physics. Means again, it's a unique value. It's a fundamental value. It is important in quantum physics as it is used in black hole and string theory. Um, One key fact about Planck's mass is that a black hole with Planck mass would have an event horizon comparable to the Planck length. So, in some way, these two are linked to each other. Meaning, if a black hole has this much mass, Planck's mass, its event horizon will have a Planck's length of what we have here 1.6156 times 10 to the power minus 35 meter, and that's kg, and that time is second, meaning it is the smallest possible black hole. Since we are talking about negative values, all of these are negative values. This and this negative values. Okay, smallest. We're not talking about something like nano, micro, or milli. We're talking about less than pico. We're going like way less than this length. And yeah, that's like all about Planck's length time. Planck's length, of course, that was our main derivation, and including that, we also talked about a little bit in the end. We talked about length and mass. Thank you.